Hi, welcome back. So, this time we're going to be specifically talking about cross validation because I actually use cross validation in code itself, but yeah, I haven't actually explained it, and I thought perhaps I should explain it. So yeah. So cross-validation is a resampling procedure, right? Used to evaluate machine learning models on a limited data sample. So the procedure has a single parameter called K that refers to the number of groups that a given data sample is to be split into. And as such, the procedure is often called the K-fold cross-validation, right? When a specific value for K is chosen, it may be used in place of K in the reference to model, such as k equals to 10 becomes tenfold cross-validation. Okay, so cross-validation is primarily used in applied machine learning to estimate the skill of a machine learning model on unseen data. That is to use a limited sample in order to estimate how the model is expected to perform in general when used to make predictions on data not used during the training of the model. It is a popular method because it is simple to understand and because it generally results in a less biased or less optimistic estimate of the model skill than other methods such as simple train test split, right? Okay, so the general procedure is as follows. So you first shuffle the dataset randomly and then split the dataset into k groups. And for each unit group, uh, take the group as a holdout or a test data. Take the remaining groups as training data set, right? And then fit a model on the training set and evaluate it on the test set and retain the evaluation score and discard the model. And last but not least, we summarize the skill of a model using the sample of model evaluation scores, right? And okay, so that is okay. Okay, so importantly, each observation data sample is assigned to an individual group and stays in that group for the duration of the procedure. That means each sample is given the opportunity to be used in the holdout set one time and used in the train and it's used to train the model k minus one times, right? So like if you choose 10 for k for the value of k, right? So it is used as a test set once and used to train the model 9 times, right? So k minus 1. Okay, and so simply put, this approach involves like randomly dividing the set of observations into k groups, right? Or faults of approximately equal size. The first fault is treated as a validation set, and the method is fit on the remaining k minus 1 faults, right? So yeah. And it is also important that any preparation of the data prior to fitting the model occur on the CV on the cross-validation assigned training dataset within the loop rather than on the broader dataset. This also applies to any tuning of upper parameters, and a failure to perform these operations within the loop, may result in data leakage and an optimistic estimate of the model skill rate. Okay. So essentially, like data leakage is just like when information from outside the training data is used to create a model, right? And this additional information can allow the model to learn or know something that it otherwise would not know, and in turn invalidate the estimated performance of the model being constructed, right? And yeah, but sometimes it can cause the model to be overly optimistic, if not completely invalid predictive models. So yeah, okay. Um, okay, so the results of a k-fold cross validation are often summarized with the mean of the model skill skill scores. It is also a good practice to include a measure of variance of the skill scores, such as the standard deviation or the standard error, right? Okay. Um, and then, so the thing is, k value must be chosen carefully, right, in the data sample. A poorly chosen key value for k may result in a misrepresentative idea of the scale of the model, such as a score with high variance that may change a lot based on the data used to fit the model, or high biased, such as an overestimate of the skill of the model. And then the three common tactics for choosing a value for k is are as follows. So the first one, we have like what we call the representative tactic. So the value for k is chosen is such that each trained task group of data samples is large enough to be statistically representative, right, of the broader data set. And we have k equals to 10, and if the value is fixed to 10, a value has been found through it is actually a value that has been found through experimentation to generally result in a model skill estimate with low bias and a modest variance, right? And then we have k equals to n, where n is the size of the data set, right? To give each test sample an opportunity to be used in the holdout set. Uh, this approach is called leave one out cross validation. Okay, and then in the data set, it's in the implementation of the code itself, we decided to use k equals to 20 because we think it is actually statistically representative enough, and we actually are concerned with okay, perhaps like uh, yeah, uh, we are actually pretty concerned with um, essentially like because the thing is, when we try to visualize like the distribution of data between like malignant or benign data in the data set, it's found that they're actually imbalanced, although the imbalance isn't actually like super skewed or something, and we think that it is actually um, the minority actually the minority sample actually is actually representative enough, if we actually use the value of 20, because it's actually pretty big, right? The whole data set is contains like 569 rows, I think. Yeah, so like if we do like k equals n, it's gonna be it's gonna be equal to 569, right? And yeah. Generally speaking, the choice of k is usually 5 or 10, but there's no formal rule, right? As k gets larger, the difference in size between the training set and resampling and subsets gets smaller, obviously. And as this difference decrease, right, uh, the bias of the technique becomes smaller, okay? And the value of k equals 10 is actually very common in the field of applied machine learning, and is very recommended if you're struggling with if you're struggling to choose a value, right, for your data set. Um, okay, and then this might work with um, wait, this might work fine with data of a balanced class distribution, but one thing to note is that the distribution is when the distribution is severely skewed, like for example, the um, the ratio is like 1 to 10, right? It is likely that one or more folds will have few or no examples of the minority class, right? But as I said before, in this case, it is actually representative enough. Like the minority class is actually representative enough. Yeah. Um, okay. Um, wait. Okay. So uh, okay, the solution is to not split the data randomly when using k-fold cross-validation or train test net. Specifically, we can split the dataset randomly, although in such a way that it maintains the class distribution of each subset, and it's called stratification or stratified sampling. Um, and the target variable y, the class, in this case, like the output, whether or not it's malignant or benign, is used to control the sampling process, right? Like for example, we can use a version of k-fold cross-validation that preserves the imbalanced class distribution in each fold, and it is called the stratified k-fold cross-validation, and will enforce the class distribution in each split of the data to match the distribution of the complete training data set, right? Okay. Um, yeah, I suppose that's it, right? Mm, yeah, so the whole point is to actually preserve the class distribution in each split, right, for a given model. And then we also have repeated k-fold cross validation, right? So like a single run of k-fold cross-validation procedure may result in a noisy estimate of the model performance. Different splits of the data may result in very different results. Repeated k-cross validation provides a way to improve the estimated performance of a machine learning model, and this involves simply repeating the cross-validation procedure multiple times, right? And reporting the mean result across all folds from all runs. This mean result is expected to be more accurate estimate of the true unknown underlying mean performance of the model on the dataset as calculated using standard error. Okay. Um, okay. So like the estimate of model performance via k-fold cross-validation can be noisy, right? And this means each time the procedure is run, a different split of the dataset into k-fold can be implemented, and in turn, distribution of performance scores can be different. Resulting in the different mean estimate of the model performance, right? And the amount of difference in the estimated performance from one run of k-fold cross-validation is another is dependent on upon the model that is being used and on the data set itself. And one solution to reduce the noise in the estimated model performance is to increase the k value, right? And this will reduce the bias in the model estimate performance, although it will increase the variance, right? It ties the result more to the specific data set used in the evaluation. Or an alternate approach will be, to repeat the k-fold cross-validation rate process multiple times and report the mean performance across all folds and all repeats. And it has the benefit of improving the estimate of the mean model performance at the cost of fitting and evaluating more models. So like, yeah, maybe it's just like computationally more expensive, like as you doing it over and over again, but it is actually able to reduce noise, right? And the common numbers of repeats include 3, 5, or 10, right? So like if you choose like to repeat it 3 times, that means on a tenfold cross validation, you to uh, 30 different models would need to be fit and evaluated, right? And that goes with like the number of repeats to be 5 and or 10 to be 50 or 100 respectively. Yeah. The approach is actually suited for small to moderately sized dataset or models that are not too computationally costly to fit, right? Yeah, because if you're talking about big data, obviously um, we don't want to yeah we don't want to um, you know repeat it, right? Because like it's just gonna be very computationally intensive. Okay, so I suppose that's it for this video, and I'll see you in the next one.